Okay, the second wave function that we're going to talk about in this second week is the function known as sound. My brethren, count it all joy when you fall into diverse temptations, knowing this, that the trying of your faith worketh patience. I hope that this week of sound doesn't try your patience too much. So sound is a longitudinal wave. Remember, there are two types of waves. There are the transverse waves, in which the oscillation is a perpendicular to the direction of motion of the wave, and the longitudinal wave, in which the oscillation and the direction are parallel. And you will remember we also discussed a couple of weeks ago that the compression of a longitudinal wave is the same as the peak of the transverse wave, and the rarefaction or the separation is the same as the trough. Now with sound waves, you have compression of molecules and rarefaction of molecules in a medium, and sound is a mechanical wave. So sound is waves that travel through a medium and are in the form of a longitudinal wave that are made up of compressions, which are shown, and rarefactions. And what's being compressed or rarefied is the molecules in the medium. And these travel and then strike the ear or whatever and form what we hear or call sound. Now, when a string is plucked on a guitar or whatever, its motion is a wave motion, and it either bunches together molecules when it's traveling from left to right. It bunches together molecules and compresses them in that direction, left to right. And then when it swings back the other direction, right to left, it rarefies or causes a rarefaction of molecules of air left to right. At the same time, the opposite thing is happening right to left. And so this movement back and forth causes a separation of molecules and compression of molecules, and this results in the longitudinal wave we know as sound, and the frequency of that longitudinal wave in the air is the same as the frequency of the string that's been plucked. Now, Boyle did an experiment to prove that sound was a mechanical wave and required a medium. And this picture basically reenacts, in a more modern sense, his experiment. He put a bell that would make noise inside a glass jar and then sucked all the air out, and basically showed that even though the bell was ringing, there was no sound because there was no medium for the sound wave to travel. Similarly, what you can do is you can suck all the air out of this jar and the phone can ring, but there will be no sound because there is no medium for the waves to travel in. Now, sound causes, or what we perceive as sound, is what happens when these waves, longitudinal waves, strike a certain aspect of the ear. And so what happens here is that compressions and rarefactions come into the external auditory canal here, and they then strike the tympanic membrane. And those of you that have had biology know what I'm talking about here. This is also called the eardrum, and this eardrum then vibrates from the energy that's transferred from the longitudinal wave, that's the sound wave. And this vibration of the tympanic membrane is then transferred to this bone right here. This bone is called the hammer. The second bone is called the anvil. The third bone is called the stirrup. And these three bones then vibrate similar to the vibration of the tympanic membrane. And this vibration then causes a motion in this fluid that's inside the cochlea. And this transfer of energy throughout from the external auditory canal where the sound wave enters to the vibration of the tympanic membrane, to the vibration of these three bones, then transfers to the fluid, to the cochlea, and this fluid is then disturbed and hair cells inside the cochlea are vibrated by the energy, and nerves pick that up and carry it to the brain, and then it is interpreted as various sounds. And so there are two types of deafness. You can have a problem with this transfer, which is called bone deafness or transfer deafness, or you can have a problem with the nerve here that's interpreting, and that's called nerve deafness. Now, one part of sound is called intensity, and the intensity of the sound is the strength of the sound waves, or the amount of energy that is transferred by the sound energy over a period of time, which is known as watts, as you remember. Energy or work divided by time is watts. And so the energy is related to the intensity that we perceive. And this is also related to the amplitude, or the amount that the string is plucked. And the harder it's plucked, the higher the amplitude, the more it compresses and rarefies the airs, and the more intense the waves sound. Now this intensity is measured in watts over an area, so it's watts per meter squared. And the intensity is proportional to the amplitude, and the frequency and inversely proportional to the square of the distance. And remember, there's several inverse square laws in physics, and this is one of those inverse square laws. That is, the intensity of a sound is related to the amplitude and the density or frequency, and inversely proportional to the square of the distance. Now, the other thing that this diagram shows is the way we measure intensity. We measure intensity compared to some absolute minimum, which is known as the zero base intensity. It's called I0. And all other intensities are related to that intensity. And each time you go above that intensity by tenfold, by 10 units, it increases the intensity tenfold, and that's what this shows here. So for example, this is measured in what's known as bells, but we talk about decibels, and you've seen decibels. So just focus on this top part. And what I want to point out is that 60 decibels to 70 decibels represents a 10 times increase in intensity or loudness, and 70 to 80 is 10 times, and 80 to 90 is 10 times. And so if you go from 60 to 90, you're increasing the intensity or the loudness by 1,000. Now, when we talk about intensity, we're talking in terms of the energy involved in this wave. Loudness is the perception of the ear. It's the perception of the intensity by the ear. So when we speak about loudness, we're talking about the translation of this intensity by the ear into something that we perceive with our brain. And so this, if you increase from 70 to 80, you're increasing the loudness by tenfold with each one of these steps. So loudness is the effect of the intensity of sound on the human ear, and it's the ear's perception of the sound, and it's a subjective meaning or subjective quantity. Now here are some examples of some common sounds related to their intensity. Now, by definition, the intensity level of 0 is the threshold of hearing, okay? So 0 decibels is equal to approximately 1 times 10 to the minus 12 watts per meter squared. And that's the lowest thing that you can hear, And so that's 0. And then you'll notice when you look at that rustling leaves is 10, you'll notice that the power increases by a little bit more than 10 times, tenfold. If it was exactly tenfold, it would be 1 times 10 to the minus 11, but it's 3.2 times 10 to the minus 11. A whisper is 20, so now it goes up 100-fold from 0. Ordinary conversation is 65, so it goes up, notice it goes up by 10 to the 4th. Then you go from 65 to 70, and it goes up about 5-fold. Goes from 70 to 100. A loud indoor rock concert is 100. That's 1,000-fold. And then the threshold of pain is 120, which is inside Rupp Arena when Kentucky's playing Florida. And I've been there, believe me. So now the second aspect of sound, in addition to loudness or intensity, is pitch. Now pitch is high or low. So it can be either something very high, which has a higher frequency, or something very low, which has a lower frequency. So as I've intimated here, the pitch that's perceived by the human ear is a function of the frequency of the sound wave. So audible sound is any sound that can be detected by the ear, and it's not a function of the pitch. It can be a low pitch audible or high pitch audible. For most people, high pitch sounds are easier to hear than low pitch sounds. Anything below audible sound is called infrasonic. Anything above audible sound is called ultrasonic. And so here we have the various sound waves and who can detect those various sound waves. And we can see that humans can detect anywhere from 20 hertz frequency to 20,000 hertz frequency. So that's called the audible range. Over 20,000 hertz, humans cannot hear it anymore. And you'll remember, like a dog whistle, for example, can only be heard by a dog or other animals. Its frequency is above 20,000 hertz. Bats use ultrasound to navigate, and so they hear this sound above 20,000 hertz. It turns out that some animals can actually detect sounds below the audible range in humans, and for example, elephants can detect things below 20 hertz. Now, the last thing I want to describe on this part of the lecture is something known as the Doppler effect. And the Doppler effect is the effect of motion on either the source of sound or the receiver of sound, or both. Now, for simplicity's sake, in this situation, we're going to say that the receiver, which are these two people shown in this diagram, are not moving. And the only thing that's moving is the source of the sound. And what you can see is the Doppler effect causes the frequency of the sound to decrease if the source is moving away from someone, and increase if the source is moving towards someone. And this is because the relative effect of the motion of the source on the speed of sound. The sound traveling toward the person that it's traveling toward is actually greater than the sound traveling away from the person it's traveling away from, and therefore the frequency changes because of that. So the Doppler effect is the change in frequency of sound wave caused by the motion of either the source, the detector, or both. The Doppler effect depends on the relative motion of the source, detector, or both. So in other words, again, for simplicity, I've kept the detectors stable. But if for example, this individual that this in the back on the left here were running toward the source, then that would cause the frequency to be changed less than if he were running away from the source. And then similarly, if the person on the right were running toward the source, that would increase the frequency, and if he were running away from the source, it would decrease the frequency. So that's the Doppler effect. If you study this diagram, I think it will make sense to you.